New observations of black hole devouring a star reveal rapid disk formation. When a star passes too close to a supermassive black hole, tidal forces tear it apart, producing a bright flare of radiation. As material form, the star falls into the black hole. Astronomers study the light from these tidal disruption events, or TDEs, for clues to feeding behavior of the supermassive black holes lurking in the centers of galaxies. New TDE observations led by astronomers at the UC Santa Cruz now provide clear evidence that debris from the star forms a rotating disk called an acceleration disk around the black hole. Theorists have been debating whether an excretion disk can form evidently or efficiently during a tidal disruption event, and the new findings accepted for publication in the Astrophysical Journal and available online should help resolve that question, said first author Tara Hung and postdoctoral researcher at UC Santa Cruz. In classical theory, the TDE flare is powered by an excretion disk producing X-rays from the inner region where hot gases spirals into the black hole, Hung said, but most TDE we don't see X-rays. The most shine in the ultraviolet and optical waves, so it was suggested that instead of a disk, we're seeing emissions from the collision of stellar debris streams. Co-authors Enrique Ruiz, professor of astronomy and astrophysics at UCSC, and Jane Dai at University of Hong Kong, developed a theoretical model published in 2018 that can explain why X-rays are usually not observed in TDEs despite the formation of an accretion disk. The new observations provide strong support for this model. This is the first solid confirmation that accretion disks form in these events, even when we don't see X-rays. Ramirez Ruiz said, the region close to the black hole is obscured by an optically thick wind, so we don't see the X-ray emission, but we do see optical light from an extended elliptical disk. The Tettel evidence for the accretion disk comes from spectroscopic observations. Co-author Ryan Foley, assistant professor of astronomy and astrophysics at UCSC, and his team began monitoring the TDE named AT2018-HYZ after it was first detected in November in 2018 by the All-Sky Automated Survey for Supernova, ASAS-SN. Foley noticed an unusual spectrum while observing the TDE with the 3-meter Shane telescope at UC's Lick Observatory on the night of January 1st, 2019. My jaw dropped, and I immediately knew this was going to be interesting, he said. What stood out was the hydrogen line, the emission from hydrogen gas, which had doubled peaked profile that was unlike any other TDE we'd seen. fully explain that the double peak in which the spectrum results from the Doppler effect, which shifts the frequency of light emitted by a moving object, and the accretion disk spiraling around a black hole and viewed at an angle, some of the material will be moving toward the observer, so the light it emits will be shifted to a higher frequency, and some of the material will be moving away from the observer, so the light shifted to a lower frequency. It's the same effect that causes the sound of a car on a racetrack to shift from a high pitch and the car comes toward you to a lower pitch when it passes and starts moving away from you, Fooley said. If you are sitting in the bleachers, the cars on one turn are all moving towards you and the cars on the other turn are all moving away from you. In an accretion disk, the gas is moving around the black hole in a similar way. And that's what gives the two peaks in the spectrum. The team continued to gather data over the next few months, observing the TDE with several telescopes as it evolved over time. Hung led a detailed analysis of the data, which indicates that disk formation took place relatively quickly. In a matter of a few weeks after the disruption of the star. The findings suggest that the disk formation may be common among optically detected TDEs. Despite the rarity of a double-peaked emission, which depends on factors such as inclination of the disk related to observers. I think we got lucky with this one, Ramirez Ruiz said. Our simulations show that what we observed is very sensitive to the inclination. There is a preferred orientation to see these double-peaked features and a different orientation to see X-ray emission. He noted that Hung's analysis of multi-wavelength followed up by observations including photometric and spectroscopic data provides unprecedented insight into these unusual events. When we have spectra, we can learn a lot about the kinetics of the gas and get much clearer understandings of the accretion process and what is powering the emissions, Ramirez Ruiz said. In addition to Hung, Fooley, and Ramirez Ruiz, and the other members of the UCSC team, the co-authors of the paper also include scientists at the Niels Bohr Institute in Copenhagen, where Ramirez Ruiz holds a Niels Bohr professorship, University of Hong Kong, University of Melbourne, Australia, Carnegie Institute for Science, and Space Telescope Science Institute. Observations were attained at Lick Observatory, the W.M. Keekick Observatory, the Southern Astrophysical Research, or SOAR, telescope, and the Swoop telescope at Las Campanas Observatory in Chile. This work was supported in part of the National Science Foundation, the Gordon and Betty Moore Foundation, the David and Lucille Parkrid Foundation, and the Hazing Simmons Foundation.